the material at the constant temperature. So for example, we austenize above 727 until it 100% become austenite, and then we bring it down to, for example, let's say 600, and then we keep it that way. So as the time pass from austenite, it will slowly change. Here it start to change into pearlite, and until we reach the completion of the transformation, so it become 100% pearlite. And also we have discussed that the temperature that we keep or we hold the material or the steel give the influence or the effect on the final product. So if it is at lower temperature, we will have something that we call benite instead of pearlite. And well, it's the effect of the fusion. The fusion. If the cooling is faster or the drive is higher, so the diffusion is more limited. Okay, so if it is more limited, so from coarse pearlite, the carbon don't have that much time to get together, so it become fine pearlite. So it just, you know, combined with the atoms, the carbon atom that is very close. So, well, if we increase further the cooling rate, so it will finally become benite. Okay, benite, which is not lamellar. The phase is the same with pearlite, but the carbon, the iron carbide, has no time to, you know, get together to form a lamellar structure. So today we will go further on this. What if we carry out the cooling at a more extreme condition? So at more extreme condition, so at first you ramp up the temperature, so the material become fully austenized, and then you bring it down. Okay, so by means of maybe water or other coolant like oil. Okay, so with this very fast cooling, we expose the material will form what we call as martensite. And I think we have came across this word martensite for a few times, where martensite indicates a crystal structure of from austenite, FCC, and having carbon that dissolve or in the crystal structure. And when the cooling is too fast, okay, instead of changing to BCC, the carbon stuck, and it formed BCT with trapped carbon. So this is martensite. Okay, trapped carbon, the carbon trapped inside the FCC that changing. So in the end, it become BCT with trapped carbon. So that is what you call as martensite. And as the temperature is lowered, we have more and more fraction of martensite. And I think this one we have touched already. And okay, so when we do when we produce the martensite, and the martensite structure is very brittle due to the fast cooling, very high stress, the carbon trapped inside. So to promote or to regain some ductility in order to facilitate or to have it to be utilized in industry to make it a more suitable material, then we have to provide some heat, or we have to do heat treatment, and which is the tempering, so that we could reduce the stress, the distortion, and we could, by doing this, reduce the cracking, the possibility for crack. So this is what we call as mar tempering. Mar tempering. We temper martensite. So mar tempering, through mar tempering, the result is tempered martensite. Tempered martensite. And another tempering is what we call as os tempering. Os tempering is the same, but instead of bringing the temperature below the martensitic transformation temperature, we just hold it at higher temperature, so it just don't cross this martensite range, temperature range. So as we hold on to the temperature, the transformation occurs, and it will result in, as it passed this line, it will result in bainite. Okay, so mar tempering will produce tempered martensite. Os tempering will produce bainite. Okay, and just a quick look for those who forget what is bainite. I hope you guys don't forget, but just a quick glimpse on what is bainite. Mana benda tu? Naik. Mana? I think, is it the slide before bainite? Pretty sure it's here, but yeah, this one. So bainite basically is for perlite. It's something like you have the grain, and then it has alternating layer of iron carbide and ferrite. So this is perlite. Okay, perlite. And bainite is like a broken lamella. It's a non-lamella, but it's the same, still the ferrite and iron carbide. And also it has needle shape. So that is how to produce the one that we have just now. The os tempering, we produce bainite. Okay, and for summary, isothermal transformation diagram make possible the prediction of microstructure product for specified heat treatment. Okay, by looking at this TTT diagram, we can predict the microstructure of the product, and we have also been exposed to martensitic steel, hardest, strongest, but it needs to be tempered to be able to regain some of its ductility to be used. And we do have another uh, another kind of phase, which is benite. So benite is something which is moderate. It's not as hard, or it's not as strong as a martensite, but it has adequate strength, and it do have uh, some ductility, even though it's not as high as perlite, but it is still good. It's still good. So another thing is fine perlite and coarse perlite. I think we have the idea of this, how to look at this, which one is strong. You just imagine the same thing, the same theory, same concept as grain boundary. As you have more interface, you will your dislocation is harder to move, harder to you know uh, to be get across to form to cause deformation. So it is stronger for the one which has finer structure of perlite. And yeah, mark tempering, as we mentioned just now, reduce the stress of the martensite, and os tempering, we produce benite. Okay, so that is one part of the story. Now we go to the next slide. Uh, okay, we go to the next slide. So before I keep on talking and talking and talking, okay, let's watch this movie first. Well, it's not a movie, just a video, not a movie. Okay, so boleh nampak? Ada, you guys can ada nampak yang saya tunjuk sekarang?
Boleh.
Boleh, eh? So okay. Okay, apa yang kamu nampak? Apa yang kamu faham dengan benda ni? Panggil sikit nama. Amsyar atas sekali nama dia. Amsyar, are you there? Okay. Spot check ada ke tak? Alright. Afiq Rohaizam. Oh, ada. Okay, alright. Apa nampak tadi video? Apa benda tu? Apa benda tu? Apa video tu berkenaan apa? Agak-agak lah. Okay. Masukkan air. Oh, cooling okay. Cooling okay. So the word cooling. Okay, so actually what the intention is to show that in real application, in real industry, we don't have that much, luxurious time to, have this wait for the isothermal transformation. We do practice if, if we need to fabricate such material for application, but normally what we do for cooling is we just dip or quench in the water. So actually what happened when we do such quenching, the cooling rate will be different at the surface and also at the center of the bulk or steel. At the surface, okay, the water or the coolant has direct contact. Okay, has direct contact. So what happened? Would be less, and the cooling rate would be less. Okay, and this gives effect on the properties of the material. Okay, as we learn just now, or maybe this would be helpful if we again take a look at this one. This one. It might be helpful if we have a look on this one. Okay. This is maybe before the holiday. So if slow cooling, it will produce perlite. Moderate cooling, benite. Rapid cooling, martensite. Okay. So what happened to this steel? At the surface, we will have very rapid cooling, so it will be martensite. The structure will be martensite. But as you go inside, the cooling rate is not that much abrupt, not that much high, or the cooling is not so fast. So we'll have perlite at the center. Okay, and to quantize this effect, so we use what we call as hardenability. So hardenability is not the same as hardness. It's not the same as hardness. Okay, rather it is a measure of depth, okay, the measure of depth to which the material is hardened after putting it through heat treatment process. Okay, let's take a look on that. Okay, so we have a steel bar. Okay, for example, we have a steel bar, say a circular steel bar. Okay, so we conduct Jomini and quench test. This is the test that you use to measure hardenability. Okay. Anyway, what you need to know is that we have this kind of jig, okay, and we have a steel bar. We have a steel bar. So we heat up this steel bar uh, more than 727 to make it austenite. Okay. So after it fully austenized, okay, after it fully austenized, so we quench at the one end of the bar. Okay, we quench. Mean that we expose it to coolant, to water, to coolant, and the resulting uh, cross section, not cross section, the resulting microstructure will reflect on the hardness of the material. So okay, so we austenized it and then we cool off one of the end. So what happened? We have a very hard area, and as we go deeper and deeper, the material will become softer. So in this test, we after we quench it, we do hardness test. We do hardness test. So if you still remember hardness test, it involves indentation. Okay, we have this, for example, a steel surface, then we have indenter, some is round, some is pyramid, like Vickers, round like Brinell, but the idea is to apply some force to make some opening or some mark, and we measure the size of the mark. That is how hardness test is being carried out. So we uh, measure the hardness along the steel bar, and we get the depth of the hard area. Okay, so this is how we measure hardenability. How we measure hardenability. Okay, kebolehan untuk mengeras. Okay, alright. So okay, and when we do such cooling, like uh, let's say uh, we have the TTT curve. Okay, and this is the TTT curve for isothermal. Isothermal TTT curve. Just now, we have been looking at this TTT curve, but now we don't want to keep the temperature we don't want to keep the temperature at one at a constant temperature. We don't want to hold the temperature, but we just put it into the water or the coolant, just like martensitic transformation. We instead of this horizontal line, the actual process or actual phenomena is something like this. The temperature keep on dropping and dropping and dropping and dropping when we put it into a cooler environment. Okay, cooler environment. So to adapt to this practice, instead of sticking up with the TTT diagram, we use what you call as continuous cooling transformation diagram, or in short, CCT diagram. Okay, so CCT diagram, it is almost the same, or maybe same as TTT diagram, but it is used or applied to a material which is continuously cooled, and instead of having this this curve, the curve is shifted a bit. Okay, so to how to say, to match the temperature, so yes, so this is how the CCT diagram looks like. This one is the CCT diagram looks like. So when we cool the material, if okay, this is temperature. Okay, this is temperature, and this is time. Okay, so the steeper the gradient means that the cooling rate is higher. Okay, so the more it goes like this, means that the cooling rate is becoming lower and lower, or slower. Okay, the cooling is slower. So if you go fast enough, you will not cross this C curve. You will not cross the C curve. Instead, you will directly enter the temperature of martensitic transformation, and this will cause your material to transform from austenite directly to martensite for high cooling rate. Okay, for high cooling rate. So you will get this A martensite, and the structure is martensite. So if you go slower, and if the cooling rate is slower, so you go along this cooling curve, and you will hit an area of austenite transforming to perlite, but you don't reach the completion. To complete, it need to reach this line. So just for a reminder, okay, this line start, this line finish or complete. Okay, so if your cooling rate is a bit fast, but not that fast. You will have some portion of perlite, and the remaining austenite will transform to martensite. So you get martensite and perlite, right? And when you go slower, when the cooling rate is slower, so when the cooling rate is slower, we will get full perlite. We get full perlite, but uh, depending on the cooling rate, if you go further slower, you go further slower means the cooling is slower. The temperature is the high temperature remain longer, the diffusion have more time to occur. So the perlite will, especially the carbon, the iron carbon, it will have time to combine more and more and more and form coarser perlite. Okay, so if we have less time, where the cooling rate is a bit higher than just now, is a bit higher, it will still form perlite, 100% perlite, but the perlite would be finer. Okay, so this distribution of a cooling rate is very much you know, it could be seen, this distribution could be seen as we go deeper into the steel bar. So the test could be like we use a steel bar, but maybe in real application just now, maybe we have seen this this steel hollow bar. Okay, you can imagine the depth. Maybe some part of it very hard. So you can predict all these things. So the deeper it gets into the material, the lower the cooling rate. And for eutectoid steel, okay, what do we got here? If we do the water quenching, you will get full martensite. This is the example of eutectoid steel. So eutectoid steel automatically 0.77% of carbon or 0.8. Well, just a matter of, I mean, I think this one is more accurate, 0.77 of carbon. You will have this kind of CCT diagram, and you just refer to the CCT diagram uh, to check the cooling of the cooling curve. If it hits the C curve, okay, or we call it critical cooling rate. If it hits, it will produce perlite. If it does not hit, okay, it just go directly down to the martensitic transformation, it will become fully martensite. So here for example, this one, okay, it goes like this. So the pearl transformation to become perlite start here. It start here, but it never complete 100%. So you cross the martensitic, and then you have a combination of martensite and perlite. And I think it's the same with just now. We're just repeating it. When the cooling rate is lower, so we get 100% perlite, and when it's lower, we get a coarser perlite. So yeah, to get, for example, for this tektite steel, if you use oil as a media, as a quenching media, you will get partial martensite with perlite. All right, and also we just mentioning this, that the carbon content gives effect on the carbon content affect the hardenability of the steel, along with any alloying element that we add, and of course the austenitic grain size. So if you use different alloy, you will how to say, if you use different alloy, of course, uh, it is very logical to to assume or to conclude or to deduct that the hardenability of the steel will be different, because you have a different what do you call that, heat conductivity and so on. So the material is different, and the material become something else. So also the carbon content is also give effect on this hardenability. And so you can check, this one is some of the example when we change the composition, when we change the grain size. Okay, this curve will be different. Okay, so I think this is repeating over and over again, but let's see this one. Application. So we are looking at the same diagram, the CCT diagram. So for the application, you can see that, for example, rotating shaft. We have a shaft which is rotating, and when it rotates, means that it maybe being supported by something, or something is touching it, maybe bearing, maybe whatever structure it is, but the surface of the shaft will experience friction, and if you aware that the friction coefficient is very much related to the hardness. Harder material is what you call wear. The wear, actually, the wear resistant. So when you when you have that friction, your material will slowly deplete due to this wear mechanism. So you want the material to be hard. You want the material to be hard for it to become high wear resistant. Okay, so for it to become something that can be maintained for longer time. So dia tak makan. So you want the surface to be hard, but because it is shaft, you know that it have something supporting it, or you have some other forces or some other stress applied. So you don't want it to lose the ductility, because hardness and ductility, or hardness or strength and ductility is something that comes in a trade-off relation. Okay, when you have a hard material, strong material, usually the ductility is lower. But if you have a very ductile material, usually the strength or the hardness will be compromised. So when we design, or when we use the material to as a rotating shaft, we want only the surface to be hard, but the core we want it to remain ductile, so that there will be no brittle fracture, no catastrophic fracture. So this is where we use the CCT diagram. Okay, we use the CCT diagram. We want to formulate the heat treatment to transform the surface to martensite and ductile core of perlite. Surface, we want to make it martensite, but the core we want to remain, we want to produce the perlite. So we have 1 and 2. So what happens here? Oh, so nasty. Okay. So you have the perlite core and martensite shell. So this material is suitable to be used as the rotating shaft. So that is one of the application, and so this is also the diagram that you want to have a look. Well, just showing that the location of the depth gives a different the cooling rate. The cooling rate differ for different bar diameter. Of course, we know due to dimensional difference, so the heat is different. The heat release and heat in and out is different, and also the position of the focusing area, even different. Of course, the cooling rate will be different, and also the use of quenching media. We use different kind of quenching media, we get a different cooling rate. This is the table. Okay, if you use in air, you quench in air, you have a slower cooling rate. But if you put into oil, the cooling rate is faster. But if you put in water, it will very fast. And the fastest is brine. Brine is salt water mixture of water and salt. So I think that is all for actually this week. Yes, this is the content of this week lecture is just this, So well, in summary, we select the steel. We have to know the hardenability, so that we know when we do some processing, some heat treatment, we know what really happened. We don't have like we fully understand the microstructure, even though in the beginning we thought that it is uniform, it has uniform microstructure, but the fact when you do some process, the microstructure will be changed. So you have to be aware of this. The material coming in form of slab maybe. So when you deform it when you do the heat treatment. You wouldn't want to, you know, assume that it's the same as the material coming in. The microstructure will be very different. Even inside the same material, each area at the surface is different. You go deeper, is different. How about the core? It will be very different. Okay, so it is very important, very essential to know the hardenability of the material, and this is done by this test. And we have a, you know, have to be able to use the CCT diagram so that we could, you know, uh, this yeah, this is constructed by this test, and we have to be able to use this to formulate the heat treatment that we want to carry out on certain part. Like just now, we carry out on the shaft, so we get a good combination of very hard surface and ductile core. So I think that is all for this week actually. So I think we finished way early, way early than we're supposed to finish at 4. So I hope you guys still with me. Ada lagi
Ada sir.
Ada doktor.
Ada. Mana tahu kan tengah-tengah hari ni dia mengantuk ke. So itulah saya punya kita punya content untuk minggu ni. I don't want to go faster. I want you to have your time to you know, revise and understand what really because iron carbon is one of the most important aspect for materials engineering, especially when we are dealing with mechanical. So one thing I have updated in the e-learning. I hope you guys can have a look. I have create an assignment for test 1. Actually, it is I need you guys to upload or send your test 1 with the reference. I'm not sure whether some of you guys remove the reference or not, because we shuffle the one for example, you guys 3 and 4 section, not me, I don't mark your test 1. Actually other lecturer will mark your, so I also mark, but I mark other section. So one of the lecturer, she you know, appeal that some of the student don't include the reference, and she just gave me all this reference. So I would like to do the same. If you guys didn't include your reference during the test 1, if you don't put, even if you put, you just send all your answer in the e-learning. And if you put, maybe you can just you know, for the sake of simplicity, just put the name test 1 underscore. If you have put in the test, we just put reference included. Okay. If you didn't put the reference during the test and you have the version of answer that include the reference, you send those something like this. So included mean you have included in the test. Okay, so yes, test one means you have the reference